Hello, everyone, and welcome to this month's topic. Today, I'm going to be looking at the time warp, or more specifically, how time is not quite as rigid and consistent as we like to think it is. And of course, the implications that this has on our universe. But within that, it's also intrinsically tied to the speed of light, and we'll see how that works in a moment. We're going to talk about why time is important, how that fits with the speed of light, how time goes funny, the evidence that we have that time goes funny, because we don't tend to see that in our everyday life. And then the importance of this, why do we care about this weird science stuff that we don't actually usually see in our day-to-day? So first, let's talk about the importance of time. So in our last session, we talked about the idea that the Big Bang Theory and how it all comes down to, it's essentially we just have evidence that the universe is expanding, and it's only by extrapolating backwards we kind of come up with the idea that the universe started somewhere and just boom for some reason. And so the evidence itself is actually in that accelerated expansion of all the matter. And so the idea of time and the speed of light are really important because they're how we measure how fast things are moving, how far away they are. And so we need to know that we can trust those judgments so that we can come up with an idea for how old the universe it is and how it all about came together. And the theories for the Big Bang and evolution in the current form, they require billions and billions of years to function. And so having this time actually has a big impact on those ideas and, you know, the common science mainstays of the day, if you will. And so typically this is measured by measuring how far light has traveled. And light obviously travels at kilometers per hour, so a distance over a time. So we need to be sure about both of those values. So if we know the speed and we know the distance, we can work out how long light's been traveling, and therefore, potentially how old the universe might be. So let's have a look at the speed of light and what we know about that and how we understand it. First things first, light is really, really fast, as I'm sure you're aware. So to get from Earth to the moon, it takes 1.3 seconds if you're a beam of light, and only 8 minutes to get to the sun. So that's a huge portion of our solar system. You can get to the nearest star in 4.4 years. And so even if you're traveling at 299,792 kilometers per second, it'll still take you 4.5 years to get to the nearest star. So that shows how vast our own galaxy is. And indeed, to get from one end of the galaxy to the other, take you 52,000 years if you're traveling at 300,000 kilometers per second. So it's really big, and light's really fast. And so light travels at this speed constantly, and so does other forms of electromagnetic radiation, because they're somewhat variations of the same thing, if you will. And so, like I mentioned before, this information is important to help us calculate these speeds and these distances. And so just to illustrate just how consistently lights travel at this speed, let's look at some examples. So I've got a jet here. This is just a regular old jet, and he's got a navigation light on his wing. And so it flashes and it emits light. And so if my jet is staying still, if it's parked on the ground at 0 miles per hour, Americans, and the light shoots out of its wing, that light is going to be traveling at 186,000 miles per second, which is the speed of light, but in different units. And so interestingly, if my jet takes off and it's flying at its max speed of 1,500 miles per hour, the light emitted from its wings still travels at that same speed. And that's kind of bizarre to think about, because if I'm standing still and I throw a tennis ball at you, it might hurt a bit. But if I get a run up and then I throw it at you, it's going to be faster again. It's going to hurt more. But light, the light doesn't follow that for some reason. Light always travels at the same speed, regardless of what it's coming from and how fast that object is moving. So that's kind of bizarre to think. So bizarre, in fact, we had to go out and prove it with science, because it is pretty counterintuitive to think about. But I do have some more information information at the link here if you'd like to see that later. And so we did confirm this with science. I'll move my head over here. And so we actually confirmed the speed of light to be constant in, I think it's the 1970s. And so we basically looked at two stars, and they were too close to each other, and they were actually within each other's gravitational pull. And so over time, they actually kind of, they do this dance and they slowly get closer and closer as the gravity of each other pulls themselves together. But that takes a long time. And for now, for our purposes, they're just spinning stars. They're just spinning around each other. And so what that means is over time, one of the stars will be going closer to us, and one of the stars will be going further away from us. And that'll happen in a nice predictable pattern. And so scientists measured the speed of light coming from those two stars, the one that was getting further away and the one that was coming closer. And they measured the speed of light for both, and it was exactly the same. We finally had that smoking gun to prove that the speed of light is the same, no matter what it's coming from and how that thing is moving. So that kind of proves the analogy of the light on the jet. Doesn't matter how fast the jet's moving, light still moves at that speed. And so that's good news for us, because if we're using the speed of light to measure stuff, we can trust that it's always going to be moving at the same speed. It doesn't matter if it's coming from a solar system or a planet that's moving that way or this way. Direction doesn't matter. Traveling at a constant speed, and therefore we can work out the distances nice and accurately. So I just talked about that stuff. So it's a nice, reliable measure, and that's what we use to kind of come up with our Big Bang theories and our ideas of the universe and what they look like. Except for one awkward thing, and that is the fact that time is not rigid. And so Salvador Dali was clearly aware of this. Time's looking pretty floppy there. And so we have this idea that time flows at the same speed for everyone everywhere. And, you know, if your life experience is anything like mine, you'd see that. And as a drummer, I know the importance of a few milliseconds here or there. So yeah, time being constant is a very important thing. But strangely, this is actually not true in all situations. Time does not always travel at the same rate for all people in all places at all times. And that's a bit bizarre. And the reason we don't notice this is because those differences are very small. You know, they're in the order of picoseconds and nanoseconds for us here on Earth, so you're never going to pick it up. You'd never know unless you had a super duper accurate clock. But when we're talking super long distances like the universe, or super high speeds like light, suddenly these small differences, they get exaggerated and they can actually become quite a big deal. So with that said, you probably still don't believe me. So let's talk some science about why and how this is true and how we even work this out in the first place. And so like a lot of things that are interesting these days, it started with, Einstein got to later, but Galileo beat him on the pump. And so this was a thought experiment. He might have done the real thing, but Galileo had an idea that basically, if there was a sailor at the top of a boat and he dropped a cannonball, basically the viewed path of this cannonball would be different depending on where you're looking from. So if you're on the boat, he drops a cannonball, it's just going to drop straight down. It's going to land on the ground. That's how physics works. But if you're on the dock and you're watching the boat go by, you actually observe the ball moving in a different path as this animation shows. So on the left is on the boat, on the right is from the dock. So on the boat goes straight down, but on the dock, we see a curve. So it's the same event, but viewed from two different perspectives. It basically travels a different path. One's dead straight and straight down, and one is a curve. And so this forms the basis for the idea of what Einstein later terms as theory of relativity. And Einstein basically said that, yeah, sure, physics works all the time, that's great, but it only works exactly as you would think if you're in the same inertial frame as that object. And so what that means is if you're on the boat, physics makes sense. If you're not on the boat, weird stuff happens. And so this idea finally helped us to unlock the ideas of why we had these great rules for physics for hundreds of years and why they work, but we could finally start explaining what the times where they don't appear to work. And it's all to do with this difference of perspectives and where you're looking from. And so in physics, what you're observing and from where matters. Sometimes it's a straight line, sometimes it's a curve. There we go. And so in terms of the speed of light, this allows us to actually prove with a thought experiment that time is not constant. And so imagine this little rectangle is a bus, and this bus is just chugging along. And this bus has a light in it. It's on the floor for some reason. But this light source shoots up and it hits a mirror on the ceiling. And then because it's a mirror, it just reflects the light straight back. So light just goes up and down, that's all it does, straightforward. And so if you're on the bus and you could watch light go really fast, if you had like superhuman watching powers, you would watch the light go up, bounce off the roof, and come back down. So it's like the cannonball, just straight up, straight down. But if you're waiting at the bus stop and the bus is going by you, like the cannonball, it's not going to follow that straight path to your vision. As the bus moves from the left to right, as shown in the bottom graphic here, the light's also going to move from left to right. It's not in a curved path because it's going up and then down, but we can see that it has a sideways movement in addition to its just straight up and down. And so combo this with what we spoke about earlier about time always moving at the same speed, and we get a strange observation. So we know that time always moves at the same place. Okay, but what about my sideways movement? If my light's gone up and down, it's moved, if my bus is 2 meters tall, my light's moved 2 meters up and then 2 meters down. But if the light has moved sideways from the observer's perspective, it has to have moved an additional distance, left or right. It's moved the 2 meters up and 2 meters down, but it's also moved however many meters sideways as the bus moves to the observer at the bus stop. And so what this means is the light has traveled further to one person than it has to the person on the bus. And because light travels at the same speed, and it's it's traveled the same speed, so the same number of meters per second, and it's traveled more meters, the number of seconds must have changed as well because the speed has remained unchanged. So if you're traveling a certain number of meters per second and that stays the same, if the meters increases, the seconds has to increase as well. And so this was a proof from Einstein that time is not the same. From the observer's perspective, it travels further and it must take longer because we know that light travels at the same speed. And so Einstein actually came up with an equation to kind of calculate how much the time would change by. And he did it with some year 9 maths, some trigonometry and Pythagoras, which is pretty cool. But this mind-bending change of perspective allows us to unlock a whole new realm of physics and time and strange things. So you might still be watching, you might still be confused, or you might still not believe me, because this is just Einstein when he's had too much coffee, thinking a lot. But we've actually proven this and observed this in the real world. So the first one was I don't know how to say that, Havel-Keating experiment. And so basically they got jets, as you do, so that's awesome. And so in 1971, one jet flew that way, one jet flew that way around the world. And so they moved really fast, they moved a long distance. And so the theory is that because they've moved quickly in different areas, different ways, the clocks that are on those planes compared to a clock on the ground, so an observer on the bus or on the boat or someone who's not on the bus or on the boat, if this is all true, their clocks should be slightly different based on what Einstein thought about before. And they found that that was true. They had these super accurate clocks, they synchronized them. And after the trip, they disagreed by 270 nanoseconds. They actually saw time changing in practice. And so there's the data there. There's a Wikipedia page you can check out later. And so they finally proved it to be real in the 70s. And nowadays we have GPS satellites, they're orbiting the Earth. And so they're traveling a long way away from us. They're traveling really, really fast. And time is very important for your GPS because you want it to be instant and happening for you right now. And the GPS satellites are moving so quickly and so far away that we actually need to account for these time changes for it to still be accurate. If we didn't use Einstein's ideas about time bending, you'd actually end up in the wrong suburb. That's how much of a difference it would have on your GPS. So not only is it true, we actually need to factor it in or we're wrong. So it's a clear and real significant phenomenon that we see, even though we don't kind of realize it in our day-to-day lives. But if you're running a GPS satellite, very important, you need to know all about it. Alrighty. So talked about some ideas, got some concrete proof, kind of lends itself to some strange ideas. And so one of these is the twins paradox. This is kind of like a classic physics logic problem. And so if you had two twins, they're both born on Earth, they're the same age, give or take. And you send one off on a rocket and one stays here on Earth. Based on what we've learned, if one's traveling a long distance really fast, say close to the speed of light, they're going to have a different experience of time. And so for the fast one, time's going to travel more slowly. So when that twin returns to Earth, after 5 minutes or whatever, the other twin on Earth will have actually aged more because their experience of time is different to the twin. And so this was thought to be a paradox. They both see each other. So how can one be old and one not? But if you think about it, it's all about those inertial timeframes. If the rocket is accelerating away from Earth, it's going to have a different experience of inertia to the person on Earth. And so it meets that requirement for those things that Einstein was talking about. And this paradox is in fact true as much as we can tell. Until we get a rocket fast enough and a couple of twins crazy enough to try it, we'll never know. But as far as we can tell, this is true because they would experience, significantly different time. And so not only is there dilation due to speed and all that sort of stuff, gravity can actually affect time. And the closer a clock is to a source of gravity, the slower time passes. And so this is a very similar concept. And with the jet engines that I mentioned before, they actually had to account for gravitational time dilation and dilation just due to speed. And so they predicted them both accurately, and both of those things caused the time difference observed. And so this is showcased in a cool movie, Interstellar. Christopher Nolan, love it. So they go to a planet. I think it's like 1 hour on the planet was like 7 years on Earth or something crazy. And so they had to get that thing done really fast because in the real world, for the rest of us, time was just flying by, and their family would die and that sort of stuff if they're there too long. And so this is actually legitimate science as far as we can tell, based on gravitational and time dilation, which operates in a very similar way to the speed examples which I mentioned before. And so this draws me to the key point of what I wanted to share today, about event horizons. And so these occur, they're defined as a boundary beyond which events cannot affect an observer. And so the one that you've been most familiar with is a black hole. So a black hole is just a super dense object. It has heaps of gravity, and so it just sucks a whole bunch of stuff in. And we know that gravity can affect time. So, okay, there's some kooky stuff going on there. And if it's, the most intense source of gravity that we know, then we're going to see the most intense effects on terms of time and that sort of thing. So gravity is actually so strong that nothing can escape it, even light. Light, for all its speediness, cannot escape a black hole. If it gets a bit close, it might bend inwards, but if it gets too close, vacuum cleaner, it's gone down the drain. And so you can think of a black hole as like a whirlpool in the water. Your boat's traveling along. If you go past the event horizon, which is like, this safe zone around the whirlpool, if you go, it's the point of no return. You're getting sucked in. You can't escape. But if you go towards the edge, you might get pulled in a bit. But if you don't hit that event horizon, you can keep going. You'll be fine. And interestingly, if you park right on the event horizon, light is stationary. So your boat can just sit there. It can be perfectly balanced between, the pulling power of the gravity or the whirlpool and the engine propelling it forwards. And so it can just literally sit there. And so it's this concept which is really key to the idea that I'm going to share from a creation scientist in a moment. And so Dr. Paul Humphreys, he's a creationist scientist. He had an alternative view of the Big Bang and the universe's origins. And so he imagines the universe as essentially being a black hole in reverse. He called it a white hole. So instead of this super massive thing, which has all this gravity and drags stuff in, it's the opposite. There's this point in the middle and that pushes stuff out. So, the Big Bang is based on the idea that the universe is expanding. And so this reverse black hole idea, kind of fits in with that and makes a lot of sense. The idea that everything is just expanding quickly as a result of this opposite black hole. But with what we know about event horizons, we know that there's this area, in the middle where, it's kind of affected by everything. There's no escape and all that sort of stuff. And given that gravity is affected by time, this could in fact result in a situation where matter inside the event horizon, whether it be whole planets or solar systems, it would have a different experience of time to what's outside it. And so as the universe, began and expanded, essentially what's in the middle could basically be frozen in time compared to the rest of the universe. Time would be traveling so slowly here that everything else is just flying off for basically billions of years on its own without us even knowing. And so this is a potential way of explaining how the Earth itself could only be 6,000 years old, as taken by a literal reading of the Bible and adding up all the family trees, and still have a universe that appears to be 14 billion years old and full of expansion, all that sort of thing. and also explains how the universe could also have appeared to expand at a rate greater than the speed of light. Because with physics, we're pretty sure that nothing can move faster than the speed of light if it has matter. And so for the universe to do that, it's a bit strange. But if we were literally frozen in time here, in our perspective on Earth, that would give the rest of the universe that time to have that, to move that far away with us without us seeing that much time on the clock. And it would also explain all those other ideas about the light coming to us being redshifted and seeing all those cosmic background radiation signals and that sort of thing. And so with the idea that time is not, it's not rigid, it can change. If we were basically frozen in time because of a huge gravitational event while the rest of the universe expanded, that would allow us to see what we observe today as the evidence that it's taken to be a Big Bang, when it could in fact be a reverse black hole that's causing that expansion instead. And so I've given a link to his paper here. That's way over my head, but the abstract and the introduction are interesting. They'll give you a good feel for his ideas, and you can kind of gauge for yourself whether you think these things are a good explanation for how we're here or not. And so I think he theorized that this happened on day 4 in the Genesis account. So it's day 4 for Earth, but for the universe, it might have appeared to be billions of years. All right, so again, what's the significance of all this stuff? We're just quibbling about distances and times and physics things. So none of these lend to direct evidence for or against the creation account of Genesis. Like I said before, some timelines are just more convenient. So for a young Earth, for a Bible, a literal Bible makes more sense, but for a Big Bang or evolution to occur billions of years makes a lot more sense. But either way, regardless of what we think and what we see, it's absolutely possible that the biblical perspective is true given the evidence that we have, and we're still learning a whole bunch of new things all the time. All right, so just to recap, we learned why time is important. It helps us to measure those speeds, those distances in the universe. We talked about the speed of light and how it's constant and how that helps us to measure those speeds and distances. But why we also need to be careful to account for time, because time isn't as straightforward as we think. So we looked at how that works and kind of, some of the things that may result from that. Just to finish up, this verse from 2 Peter 3:8 says, "But do not forget this one thing, dear friends. With the Lord, a day is like 1,000 years, and 1,000 years are like a day." And there I've got some references at the end, talks about the constancy of the speed of light, those experiments that prove time dilation, and then Mr. Humphreys' paper there about the reverse black hole, if you will. So thanks for tuning in this time, and I'm looking forward to see you guys for the next session.